What did I tell you? 88 miles per hour! Next Saturday night, we're sending you back to the future.
Okay, all right. Saturday's good. Saturday's good. I can spend a week in 1955. I can hang out. You can show me around.
Marty, that is completely out of the question. You must not leave this house. You must not see anybody or talk to anybody. Anything you do could have serious repercussions on future events. Do you understand?
Yeah, sure. Okay.
Marty, have you interacted with anybody else today besides me?
Yeah, well, I might have sort of bumped into my parents.
Great Scott! Let me see that photograph again of your brother. Just as I thought. This proves my theory. Look at your brother.
His head's gone. It's like it's been erased.
Erased from existence.
Whoa! They really cleaned this place up. Looks brand new.
Now remember, according to my theory, you interfered with your parents' first meeting. If they don't meet, they won't fall in love, they won't get married, and they won't have kids. That's why your older brother's disappearing from that photograph. Your sister will follow, and unless you repair the damage, you'll be next.
This sounds pretty heavy.
Weight has nothing to do with it.
What I wanted to talk about was Einstein's theory of relativity, because it ties in with the speed of light, synchronicity, conventionality that you were talking about earlier. Briefly describe what relativity is, what the theory of relativity is.
Relativity is the branch of physics that was discovered by Albert Einstein. There are two sort of subdivisions in relativity called special relativity and general relativity, and special was discovered in 1905, and then in 1915 he discovered general relativity. Basically, they're the branch of physics that deals with the unusual effects that happen when an object travels at very, very high speeds or in a very intense gravitational field. The special theory of relativity ignores gravity. The general theory includes gravity. And so what Einstein discovered was that space and time are a little different than what most people think they are. They're not sort of absolute and the same everywhere. Clocks don't. Our natural expectation is to think that clocks all tick at the same rate if they're well constructed clock. Okay, you got a good one. You got a Rolex, and it's going to take a licking and keep on ticking, right? The assumption is that no matter how you move, it doesn't affect the rate at which time flows. And the effect indeed is so small that we don't notice it in our everyday lives. But Einstein was able to figure out rationally from really just two observations that time is affected by motion. The flow of time, the rate at which clocks tick, is affected by motion. And also lengths are affected by motion. And so, how thick you are depends on how fast you're moving. That's kind of interesting. And again, it's not something we would notice in our everyday experiences because the effect is very small. It's not until you get up to a substantial fraction of the speed of light that the effects become significant. But that's really what it is. It's the physics dealing with very, very high speeds or very intense gravitational fields.
So the theory of relativity is that time and space or matter are relative to what?
They're relative to the speed of light, interestingly, and the round-trip speed of light. One of the peculiarities that was discovered in the late 1800s is that the speed of light, no matter how you measure it, the round-trip speed of light is always 186,282 miles per second. And that's very peculiar. I want to give you an example of this. Suppose that you're in a car and you're driving 50 miles an hour, and somebody in the back seat takes a baseball and throws it, and they're capable of throwing a baseball at 50 miles an hour, and so they throw it out the window. Now, someone on the sidewalk would see that ball traveling at 100 miles an hour, wouldn't he? Because it would be the speed of the car plus the speed of the baseball. It would be 100 miles an hour. That's called the Galilean velocity addition theorem. Okay? You just add the velocities. But what's peculiar is light doesn't work that way. If I'm traveling down the road at half the speed of light, and I turn my headlights on, and they're moving the speed of light faster than me, which is c, I'm traveling at half c, you'd think somebody on the sidewalk would see the light traveling at 1.5 c, 50% faster, but he doesn't. Somehow he sees the speed of light as c faster than him, whereas I see the speed of light as c faster than me, even though I'm moving relative to him. Very peculiar. And Einstein realized that the resolution to that paradox is entailed by the fact that my clock doesn't tick at the same rate as someone on the sidewalk, and so the way I measure time's different, and lengths change, and so the way my rulers are not the same as a person's who's stationary on the sidewalk.
So if you're traveling at 3/4 the speed of light, your ruler is different than the man standing on the sidewalk right next to you as you pass by.
Right.
If you could take a snapshot from a neutral perspective, your ruler and his ruler would be different lengths, even though they might be 1-foot rulers.
That's right.
Because you're traveling at the speed of light, therefore, the length of everything relative to you has shrunk. Correct?
Yes. And the thing that's surprising to people is when you're moving, you do not notice any of these effects because everything shrinks together. Okay, and so you might say, well, this roller seems just as long as it used to be. It's still the length of my arm, but that's because your arm is also shrunk in that direction, and so on. So everything moves together. Your time might be slowed down, and so you're moving very slowly, and your clock is ticking very slowly, but you don't notice it because your brain is slowed at the same rate your watch is. And so everything slows together. And so you don't notice the effects in your own car or in your own spaceship or whatever you're in that's moving at some substantial fraction of the speed of light. But somebody watching you with the telescope would notice that inside your chamber there, you're moving very slowly. And the faster you get to the speed of light, the slower and slower time flows.
So give us a thought experiment with the traveling to a distant star, say Alpha Centauri, traveling at the speed of light. What would the effects of that time dilation and that space dilation be?
So as you move closer and closer to the speed of light, since time slows down, you age very slowly. But from your perspective, it doesn't seem that way. It seems like time's flowing normally. But from your perspective, as you're moving very fast, you're always allowed to consider yourself stationary, you see. I mean, we don't feel like we're moving, do we? We're in this room, we're on the Earth, the Earth's rotating, and we're moving at 700 miles per hour relative to the center of the Earth in a easterly direction. And then we're orbiting around the sun at 67,000 miles per hour. You don't feel that, right? Because it's a smooth motion. So the person who's in the spaceship, from his perspective, it's the universe that's moving backwards at a substantial fraction of the speed of light. So from his perspective, since things shrink in the direction of motion, that star that was very distant is now not so distant because the universe is compressed in the direction of motion, interestingly. And so what happens, let's say it's a star that's, say, 4 light years away. Alpha Centauri, the nearest star, is 4.3 light years away. So you'd say, well, it's going to take at least 4.3 years to get there because we can't move faster than the speed of light. We can only move slower than the speed of light. So I move up to a very high speed, as closest to light as I can get. The person on the ship would be able to make the trip in, say, a couple of months. Because from his point of view, the universe shrank in the direction that he's traveling, and so that it didn't take very long to get there. Now, a person on Earth would say, no, the reason you were able to make that trip in what seems like 2 months is because your clock was running very slowly. And so they both agree, everybody agrees that they're able to make the trip the astronaut is able to make the trip aging only a couple of months. They disagree on the explanation for why, because the explanation is relative to the person's point of view. So that's where it gets its name.
So twin astronauts, one stays on Earth, one gets in a ship and heads off to Alpha Centauri, makes the trip there, and comes back. What happens?
So if he comes back and meets his twin would have aged 8.6 years, whereas the astronaut would have aged barely, 4 months, say, depending on the speed. So the twins are now different ages. So very interesting.
Is traveling at the speed of light possible? And if not, why not?
So it turns out traveling at the speed of light is not possible unless you're light. Okay, light travels at the speed of light. Anything that has no mass has to travel at no rest mass has to travel at the speed of light. Anything that has mass, though, can't ever reach it because there's a third effect that kicks in. We talked about how lengths compress as you go faster and faster. Your time slows down as you go faster and faster. The third effect that kicks in is mass increases. Mass goes up. Things get heavier, and so and when something's heavier, it takes more force to accelerate it. And so it turns out that in the limit, as you approach the speed of light, your mass would go up to infinity, and it would take an infinite amount of force to get you any faster. So you can't ever push something up to the speed of light. You can get arbitrarily close, but you can never reach it.
And if you reach the speed of light, or you got close to the speed of light, is time travel possible?
Well, in a way, yes, because in a sense, we're already traveling through time because, I'm going from 12:45, 47 seconds to 48 to 49. We're moving forward in time now. Now, the interesting thing is you can increase the rate at which you move through time by simply moving through space. And so if you wanted to, you could travel at a very close to the speed of light out to a distant star and come back, and you could see the future of the Earth. You could come back. It'd be 100 years later here, but from your point of view, the trip only takes a couple months. So that's a type of time travel. But if you wanted to come
Hold on
back,
a second. Say that again, because yeah, let's just say that again. I'm not gonna admit how stupid I feel after that. So you could travel 2 months at near the speed of light, or at
Yeah.
the speed of light, to someplace and come back.
Yeah.
When you got back, you would be 2 months older.
Yeah.
But everybody here would have been. You would see your grandchildren and maybe your great grandchildren.
Yeah.
So you would be traveling into the future of our planet, but not your future of you.
yeah,
Okay.
yeah, you got the right idea. That's it. So
Can we travel to the past?
Effectively, you're aging, and there's the problem. You say, well, okay, I want to come back and tell my wife about this, that I met my distant kid, but I'm sorry, she's dead, and there's nothing you can do about it. You can't go back. Because in order to go back in time, you'd have to go faster than light. If you can go faster than light, you can go back in time. But
So
you can't go faster than light. Therefore, you can't go back in time.
Are you telling me that Endgame and Back to the Future are not
Sorry,
actual possible?
it's not gonna happen.
What is the
not gonna
logical problem with traveling back into the past, and why does that logical problem mean that we can never go back in the past?
Well, one of the issues is sometimes called the grandfather paradox. In principle, it would be, if you could go back in time, in principle, you could, although it would be ill-advised, you could go back and assassinate your grandfather before he ever even met your grandmother, in which case your father's never born, in which case you're never born. But if you're never born, then how can you possibly go back and assassinate your grandfather, you see? And so you end up with a paradox. On the one hand, you must exist in order to cause his death. On the other hand, you can't exist because he died. And so it leads to a logical contradiction, and that which leads to a contradiction is false. Therefore, time travel into the past is false.
Did you catch the logical math behind that, everyone? Okay.
Back to the Future, basically.
It's false.
Yeah, it's not going to work, but it's a good movie. It's fun.